All right, there we go. Hello, 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 everybody. Hello, hello, hello. All right, we're back. Okay. How's everybody today? How's everybody doing today? Hopefully you're doing okay. All right. Yeah, get started here momentarily. 6. Hey, Golmash, how are you? I hope you're doing well. Hey, Brenton. I'm glad you're well. I'm doing very good. Very good, thank you. It's been a nice day so far. It's a nice morning. I can't really argue with what's going on right now. Hopefully it'll be even a better day. Hey Chase, how's it going, my friend? I hope you're doing good. It's been a very nice morning so far where I'm at. So hopefully working hard or hardly working, just depends on which one you want to call it. What a relaxing day today. I don't know what it is about today, but things feel pretty good. How's everybody here? We're going, hopefully doing good today. Doing good. I see a few more people start to trickle in, so that's good. Let's see how this works. Not putting a lot of faith in the. All right. We got a few people in here, so that's good. Chase, I'm glad you're doing very well, my friend. Down, glad you're doing really well. It's a nice chill day today, so gonna have another relaxing day, I hope. Go ahead and turn down the music here just a smidge. Doesn't have to be super high. 1.5. There we go. All right. Okay. We're about ready to get started here. So, all right. Hopefully everybody's ready to go. Let's give it a go. Yeah. Okay. Okay, let's get started today. Welcome back. Welcome back to Wednesday. All right, end of the week time today. So today, what we're going to be covering here is going to be the end of chapter 10, or chapter 10, I should say. Good day in the UK. We come out of lockdown today. Yeah, that's what I'm talking about. Less lockdown, more walking around a little bit. I'm hoping, hopefully, the vaccine comes by soon. So, all right, so what we are doing here today is we're going to be covering today the basics of trigonometry. Now, let me go ahead and ask here for that. Oh, I see Keisty's in here. Now I'm afraid. All right, so just kidding, my friend. uh, okay, so what we're going to be covering here today is trigonometry. All right, so trigonometry here is going to be the last part here. Now, I want to go ahead and ask you guys here really quick about if you'd like me to do just the first two sections here. The reason why is because the third section here is pretty heavy with how we apply what we're going to talk about in the first two sections. So I don't want to kind of overwhelm you with a lot of information all at once. Um, but typically I like to do the last section kind of on its own. But I'm going to leave it up to you here. What would you guys like me to do? Actually, let me make a little poll here. Because I am definitely going to do the first two sections here without a doubt. So those two sections are definitely a go. But usually when I do this, yeah, split it up? Okay. Yeah, usually when I do this, it's usually a lot of information all at once. Hey, Taurus, how are you doing? Do I teach at university? Do I teach at university too? I teach at community college, Taurus. I teach at two community colleges. Surprisingly enough, things that some people may not know is that I actually work part-time at two places. And I've done so for 10 years. And can't really argue with that whatsoever. I love teaching, so it's all good, man. I have a lot of fun doing it too. So, and that's what you should be looking at. You know, something you find fun. Dr. Dan slept it up, man. All right. Well, I just kind of asked the question here, Dr. Dan. If you want to split this up into two parts, so we would do 10-1 and 10-2 today, and then do 10-3 for for next week. That would be the effective end of the book. Or do all three sections here today. There's just kind of a lot to do in section 10.3. So that's why I'm kind of putting that out there as a potential choice. Again, I'm not here to force decisions. I always like to do democratic process involve. It's one of those things that I kind of like the most. So democracy kind of rules, I suppose. We put up a poll here so we can see exactly how this works. I see some people's choices, but all right. So there we go. I put up the poll there, so it's at the very top there of the screen. And go ahead and put that in. And then I'll go with whatever you guys put here after the poll ends. So, or if it's overwhelming. So, fair is fair. I like fairness. Fairness is very important. So, split, split, okay. All right, got about a minute left here. In the meantime, go ahead and get this going a bit. Where is it? Okay. Need to just bring up some word here. There we go. Got it. And word is all the way over here for okay. Perfect. Okay. Have you ever read that should be Euclid's, right? Elucid is you mean Euclid's Elements? I mean, I've heard of Euclid before. I mean, I don't think I've read the book. I've studied Euclid quite a bit back in the day. pretty sure if I thought back to my undergrad days with Euclid and actually working with that, how they came up with pi and things like that as the ratio of circumference. All right, so what do we see here? We got 2. All right. All right, 2 it is. There you go. All right, so 2 sections here today. Okay, so I do want to point out here, again, we're just going to do the first 2 sections here, 10.1 and 10.2, and then we're going to just spend the entirety of next week, next Monday, I should say, on just that last section there so we can start putting 2 and 2 together. Okay, all the homework, all the tests there are all open, available for you, so feel free to work on those until the end of the semester there. Okay. In any case, let's go ahead and talk about several things. Let's go ahead and switch up here. Bam. Okay, so let's talk about today a little bit of trigonometry. Now, before we talk about some trigonometry here, we got to talk about some practical things that are certainly applicable to trigonometry, such as angles and right triangles. All right, so that's what we'll talk about here first. So again, section 10.1 here, talk about angles and right triangles. Okay, so let's discuss a few things here, at least to start off with. Now, if you remember what we did here in one of the previous sections, we talked about degrees, minutes, and seconds. And so we're going to want to talk about degrees, minutes, and seconds here once again. So what we're going to be looking at here is we're going to be specifically looking at how to convert degrees, minutes, and seconds to decimal degrees. And we'll also look at it vice versa. Okay. We're going to look at degrees, minutes, and seconds, and we're going to convert it. We're going to convert it into decimal degrees. So let's take a look at an example here, and let's see how we go ahead and attack these kind of problems. That's okay. You didn't miss anything, JC. We're just gonna, the only thing you missed here is that I put up a poll here about how many sections we're doing today. The class decided we're gonna do 2 sections here today just because of the heavy content of the trigonometry here. I think doing 2 sections and then today and then 1 section as the last section here of the textbook here for next time will give a much better understanding about how we're going to be using it. So I don't want to put too much information, but I had to ask the class first before I went ahead and did that. So otherwise, we're just getting started. So, okay. So let's talk about degrees, minutes, and seconds here. Put DMS here for degrees, minutes, and seconds to decimal degrees. Okay. So the first thing that we want to do here is at least what we need to understand is what the key is here specifically. So the key here specifically is going to be revolving around the idea that when we talked about degrees, minutes, and seconds, we said, okay, well, 60 minutes equals 1 degree. Okay, we know that for a fact. And we know that, of course, 60 seconds here is equal to 1 minute. So just like regular time, there you go, simple enough. Now that also has other implications as well. Now if we want to go to decimal degrees here, we're going to use these 2 conversions because we could basically kind of go backwards here just a little bit. Meaning to say, if we looked at 1 minute and we put it in terms of degrees, well, 1 minute here is, oops, all right, 1 minute, let me write that a little nicer. 1 minute is equal to 1/60th of a degree. Okay, so 1/60th of a degree here is equal to 1 minute. And if we look at 1 second, and we break that down in terms of minutes, again, using the conversions that we have here, we actually get 1/3600th of a degree. Good afternoon, Crevette. I hope you're well. How are things in France, my friend? I hope they're really nice. Okay, so we have 1 minute is equal to 1/60th of a degree, and 1 a second is equal to 1/3600th of a degree. So, what is the lesson? The lesson is today talking about angles and right triangles and putting together some trigonometry. So that's going to be the lesson here for today. So some basics here for sure, and I'm sure is very applicable to physics concepts. So I think you'll learn a little bit here for sure. So let's go ahead and take a look here at an example. We'll do a couple of them. So let's say we have 37 degrees. Perfect. That's all I ask for, my dude. 49 minutes and 52 seconds. Okay, so let's say I want to convert that into decimal degrees. All right, so what we're going to do here is just break it down into one step at a time. All right, all we want to do here is we're going to take the 37, that's going to be its own thing. Okay, so 37 is going to be separate. The next part here is we're going to convert minutes into degrees. Now, because we know that 1 minute is equal to 1/60th of a degree, we're going to go ahead and take that 49, we're going to put that 49 and put that over 60. Essentially, you're just multiplying 49 times 1/60th and you get 49 over 60. Finally, we have 52 seconds. So 52 seconds here is going to be 52 over 3600. And so all we're going to do here is just go ahead, again, bip bop boop in the calculator there. Okay, nothing too fancy going on there. All right. And so we have 37 plus, again, don't forget to put the parentheses there, so 49 over 60. And then plus another 52 over 3600. And so here in this particular case, we get a pretty nice one here. I just made this up on the fly. But you get 37.831 repeating degrees. Okay. So if you got that same answer there, then that's exactly how you want to approach that problem. Okay. That's pretty much all you have to do to convert from decimal to degrees, minutes, and seconds. Or from degrees, minutes, and seconds to decimal. Sorry, I'm thinking a little ahead. Are there any questions about that example? Or do you want me to do one more? Just do another? Okay, no problem. Let's go ahead and do another here. All right, so let's write down, let me go ahead and make this up here. It makes it a tad bit easier. Actually, let me zoom this out here. Just a moment. Make this a tad bit bigger here. Or a little more space. All right. In any case, let's put in 98 degrees, 33 minutes, and 23 seconds. Okay, so 98 degrees, 33 minutes, and 23 seconds. We want to convert this into decimal degrees. Okay, so let's put this together here. All right. Actually, let's try it this way. Let's take about a minute, and then let's have you give it a try. Okay. So go ahead and you can write that workout. I'm going to write the workout here in just like 30 seconds to a minute. Okay, so let's give it a try on your end, and then we'll do it together here. And hopefully you can get the same results that I'm going to get here once I go ahead and show off this problem. Hey, Taurus, thank you for the follow, my friend. All right. I know that's maybe not quite 30 seconds, but that's okay. Let's hope that you get the same thing that I'm going to show off here. All right. First and foremost, oh, you got to that 98.5564 degrees. All right. That's what Crevette got. All right. I like that. Looks pretty good. Let's see if Crevette is definitely right on this one, but it looks good. I will say that. So we get 98 plus 33 over 60. Got that too? Ooh, all right. I think we're in great shape. I put 23 over 3600. Okay. Again, I fully expect you to use a calculator for this part, but let's go ahead and confirm that to be the case. 23 over 3600. And indeed, that is correct. Okay, so that correct answer is 98.5564 degrees. Spot on. Very nice. All right. So if you got that too, then you're in great shape. Okay. Nice job. All right. Now that we're getting there, good, good, good. All right. Let's go ahead and move on here. Let's move on here to the next part. I know, right? It's like magic. See, that wasn't so bad. Once you have the keys down here, it's not as bad as it may seem. All right, now let's say we want to work backwards, okay? So this time here, let's go over the next part here. So the next part here is basically doing decimal degrees to degrees, minutes, and seconds. Okay, so that's going to be the next part here. Okay, so let's work with this. All right, so we got to work backwards here. So it's like if I want to work from 98.5564, and I want to get it, put that into the approximate degrees, minutes, and seconds here as a result. Now we're going to use this key that you see here from before. You're definitely going to use this key here, but we're going to use it in a slightly different way. All right, so let's talk about the big key here in this process, though. The key here is to basically multiply by 60 twice. Now, I haven't exactly told you how multiplying by 60 twice is really going to be helpful, but let's go ahead and take a look at a couple of examples here, and let's work through it. Okay? Okay, now, let's look at the first example here. So the first example here is, let's just make one up here. All right, 43.17892 degrees. Okay, I just made this up, so it's like, here it is. I made it up. Yeah. Yeah, there it is. Oh my gosh. All right. Okay. In any case, 43.17892 degrees. Now, what we're going to do is, if we want to go ahead and find out what the minutes and seconds are going to be, we are going to use this key here. But before we do that, we're going to need to separate the 43 out. So let's just imagine the 43 is a separate guy. All right. So we'll have 43 degrees with something minutes and something seconds. I.e., one of the things to keep a note out about this is, come on. Oh, right. Better do that. All right. So one of the things that we want to keep here, let's talk about key number 2 here. Key 2, only focus on the decimal part. Okay. So this is going to be the big thing to kind of keep in mind here. We only want to focus on the decimal part here. So I don't care about the 43. It could be whatever number you want it to be. But everything to the right of that decimal, yeah, that's actually what I care about here. So let's take a look here. I'm going to focus on the 0.17892 part here. Okay. And so what I'm going to do here first is I'm going to go ahead and multiply by 60. Remember, the key says to multiply by 60 twice. So this is my first iteration of multiplying by 60. So let's put that in the calculator there. Let's see what we get. Okay, so what you should see on your calculator here is 10.7352. Okay, now this is very important here. Okay, we're not quite done just yet, but what I am going to do here is I'm going to take this 10. There's no rounding involved, by the way, no rounding. So I'm just going to take the 10, and those are going to be my amount of minutes that I have here. So I have 10 minutes, just like so. Okay. And then what I have to do is now take the decimal portion that I have of this particular answer. That looks pretty good. So I'm going to take the 0.7352. And we're going to multiply that by 60. And we're just going to take a look at that answer as well. So again, on your calculator here, 0.7352. Multiply that by 60. All right, you have 45 minutes there. So here we get 44.112. Excuse me. Let me check that real quick. Okay, fine. So we have 44.112. And so if we want to find the most approximate, we just take this 44 here. I'm going to put that in right there. 44 seconds. I'm not sure here, Crevette. Do we actually round up regardless? Or do we actually just keep that the same there? There's always a debate about that, to be perfectly honest. So 45 could be easily correct as compared to 44, depending on the circumstance. I just usually take what's in front, and then they just kind of run with it. But rounding up could be appropriate as well. I'm just looking at a practical side of things. All right. Let's go ahead and try another problem, though. And I'll wait for Crevette's answer here. So I'll wait for Crevette's answer once he gets that put together. But we'll put another example down here in the meantime. Okay, let me get that out of existence. Okay, I'm going to do another example here. Now this time here, for you guys, we're going to have you guys give it a try. We'll take a minute, okay? We'll have you give it a go. I missed my touch. Oh, okay. So it was supposed to be 44. Okay. All right. Fair enough. Fair enough. All right. So let's try 67 degrees. 67. What am I doing? I'm thinking about the weather. 67.816459. All right. All right. 67.816459. So let's take a minute here. Let's go ahead and find that in degrees, minutes, and seconds. Okay, using the process that you see here on the screen. And then hopefully you'll get the same answer that I did. So let's go ahead and do that. okay. No problem, Crevette. Hang on a second. There we go. There you go, my friend. Have a wonderful night, Crevette. Please enjoy yourself. $67 degrees, 48 minutes, and 59 seconds. Okay. That looks pretty good. Kind of like that. Let's see if you guys, maybe that's the answer there. That looks pretty, that sounds really good though, from where I'm just kind of ballparking in my head. Okay, well, let's take a good look here and let's see it in action, right? So, okay, we spent about a minute. So, again, the 67 here is going to be separate. So we're just going to leave the 67 alone. There it is. Fair enough. Now, let's go ahead and take a look here at the decimal parts. So we get, you got the same? All right, Brenton. All right. So we got two of the same answer here. So I'm crossing my fingers that this is indeed going to be our good to go portion of the program. So we're going to multiply by this decimal part here by 60. So let's see what we get here. So here we get 48.98754. So indeed, we're going to just take that 48. So far, so good. Get 48 minutes, spot on. Okay. And then we're going to take the 0.9875. And we'll multiply that by 60. Wait, 98754, pardon me. That should be 0.98754. I missed the last decimal there. My fault. And here we get 59.2524. All right, we'll just take that 59, and there we go. That's correct. Nice job, guys. Absolutely spot on here. 67 degrees, 48 minutes, 59 seconds. Great work, everybody. Very nice job. You guys are really picking up on it. So very, very happy to see that. Okay, any questions about that so far? Yes. Yes. Nope. Okay. Let's focus on the next part here then. Okay. I'm going to move forward. So blank out of existence here. All right. So next what we're going to talk about here is we're going to now talk about, since we're talking about angles here. Now most of you guys are very familiar with angles here in degrees, or now with even degrees, minutes, and seconds. But there is an additional way to express angles here besides both of those. And we're going to explore the final way what we want to discuss here today. And for at least expressing angles, not the last part. But we want to talk about the concept of radians. Okay. So radians here is basically a way we can another way to express an angle measurement, and does certainly have applications that we'll see just right after this. Okay, so we're going to see a couple of a couple of applications as well about where radians fit in. Now, what we need to do is we need to first discuss here how radians work. So what we need to do here first is we want to convert from our good friend degrees. Okay, so let's go from degrees to radians. Okay, so we want to go from degrees to radians here. So the first said conversion here. Okay, now for us to do that here, we're going to follow a very specific conversion. All right, and that is radians, whatever radians that we get here, is equal to the number of degrees, whatever those degrees are, and we're going to multiply that by pi over 180. So to convert from degrees into radians, we're going to take the number of degrees, whatever it is, multiply it by pi over 180, and that will reflect the number of radians that we actually have. Now, what I'm going to show you next here is like, okay, here's the formula, but we obviously have to apply it. Now, this example I'm going to show here next is going to be a rather important example because it does highlight a couple of things here that I do want to kind of showcase. Okay, so let's go at it like this. Okay, I'm going to start off with something really easy, and you'll see kind of what we're working with here. Let's say I had our particular friend 90 degrees. Okay, 90 degrees, very simple to use. Everybody know that the right angle. Yeah, it is what it is. Fair enough. Okay, now with 90 degrees here, all right, we're going to want to convert this into radians. So the radians here for 90 degrees, actually, we're going to have the number of radians here is equal to 90 times pi over 180. Now, admittingly, yeah, okay, that's very good, JC, that's correct. Admittingly, you could actually bip bap boop that in the calculator and you'll get a decimal equivalent. And by and large, that's not too hard. But as JC has correctly pointed out here, if you take 90 over 180 here, you can reduce that down as a fraction. Again, it would look like this, like 90 pi over 180 if you multiply it out. But you can actually reduce this as a fraction. 90 goes into 180 two times, and so what you could actually be left with is pi over 2. Okay, so if you can reduce the fraction down, and this is kind of like one of the things I want to talk about here really quickly, is that if you can reduce the fraction down, leave the pi alone. Okay, so just leave the pi alone, unless you know, unless it's like decimal degree. If it's decimal degrees, like 90.7327, yeah, you're gonna get a pretty messy number. Okay, without question. Right, you're not gonna get a nice fraction. But if you can reduce the fraction down, leave the pi alone. That's basically my point that I'm trying to make in this first example here. Okay, if you can't, okay, just put it as a decimal and you're perfectly fine. But this is the best practice about how to convert, say, degrees into radians that everybody technically uses. So you can reduce it down. It may be a weird fraction, but it's a weird fraction. Run with it. But if it's just like super messy and it just makes no sense, then just go ahead and put it as a decimal and call it good. You'll be fine. Let's look at another one though, because I did that one really quick. So let's try 135 degrees. So let's try 135 degrees. What's 135 degrees? What would that be as radians? Let's take about 30 seconds to try this problem out. Okay, so you took a short amount of time. That's perfectly fine. We'll see if you guys get the same result that I do. That's okay. We're going to take 135. We'll multiply that by pi over 180. Again, pretty sure we can go ahead and convert 135 over 180. All right. And you could reduce that down. You could, again, reduce it down on a calculator, whatever the case may be. And if you do reduce 135 over 180, just that part there, leaving the pi alone, just ignore the pi part there, then indeed you're going to get 3/4 here. Okay? That part is correct. Okay, so we're going to get 3 pi over 4 will be your radian equivalent. Good, that's correct. Nice. Okay, so by and large, not too hard. There it is. Okay, questions about that so far? Cool, nice. Okay, now, this time, let me go ahead and erase this here. Let's say, I'm just going to erase all this. Okay, next, what we want to talk about here is we want to talk about how to convert here backwards. Okay, so let's say we want to convert backwards here. So let's say I want to convert from radians to degrees. Okay, so that's the next one here on the agenda. Now we go backwards here, radians to degrees. So if we want to go from radians to degrees here, all right, the number of degrees something is, we're just going to use like it's very similar to the last conversion. It's going to be the number of radians, only we're just going to flip over that fraction. Instead of pi over 180, we're going to take 180 over pi. So I'm just going to flip that over, just like so. So let's do a quick example with this. So a quick example is, let's have you guys give this one a try and see what happens. But let's try 11 pi over 6. Okay, so let's try 11 pi over 6. Now, one thing that we'll just keep in mind here, if you take 11 pi over 6, and you multiply that by 180 over pi, the pi's here will cancel out. So again, the pi's will cancel out fairly conveniently, and then it'll just leave you with what you need to multiply and divide by. Anybody have an answer for this one here? $330. Oh, wow. Okay, you guys are on the ball, man. Holy crap. All right. $330. Very nice. Okay, good stuff. All right, that's correct. Very good. Okay, great. Are there any questions about that? Hopefully that one's pretty straightforward. Nope. All right, sounds good to me. Okay. Easy peasy lemon squeezy. Okay, Now, let's move on to the next part here. All right. And let's talk about some applications for radians here. Okay, so let's say we want to convert from we want to use radians in several applications. All right, so let's talk about that here next. This part here is actually really super simple, so not too shabby. Like I said, a lot of information dump here today, so do apologize. Okay, next we're going to talk about sectors of a circle. Okay, so we're going to talk about a sector here, and we'll talk about circles. All right, now for a circle here by itself, albeit it's not too hard as you can probably figure out, but I'm going to look at two aspects here when it comes to the circle. So let's go ahead and take a look here. Here's our circle. Over a bit. It's widened. All right. So we're going to look at two parts here when it comes to the circle. Okay. So I'm going to go ahead and find that here in just a second. All right. There we go. Okay. So the first thing that I'm going to look at here specifically is I'm going to look at this part right here. So let's say from this end all the way over to this end of the circle, this part here we're going to call S, okay? Now S here, what does S represent? S will represent here, and will represent the arc length of the circle. So the best way to kind of think about arc length is that imagine, if you will, you actually figured out how long the crust of a pizza was. Okay, so you said you just look on the outside, the curvature of the pizza, as opposed to the inside there. So you say, okay, well, how long is that? You know, how long is the length of that crust, for example? It's the best way to kind of put it here. Now, for arc length here specifically, we do have a formula, and that formula here is rather important. So for arc length here, which we'll label as S, because again in the book it's also labeled as S, this is equal to two things here. So I'm going to label this within the circle. So we first have a radius r, and we also have a here. Have this angle inside here, a. Call it little a. This is going to be r times a. And then go ahead and state what r and a are, just really fast once again. So r here is the radius of the circle. However, the more important one here is a. A is the central angle of the circle. So the central angle of the arc in radians. So this is very, very important, all right? A is the central angle of the arc in radians, all right? So we want that in radians, all right? Very, very important. So we can't use degrees straight up. And that's the biggest mistake people see in these problems is they go ahead and they look at that and they're like, oh, yeah, it's just going to work out this way. And the answer is no, it's not going to work out the way you thought it would. Okay. So have to be a little bit extra careful there. Now, we also have one more thing to take care of, and that is to say, okay, well, what about the area of the sector of a circle? Or what about, what about the area of a slice of pizza, for example? So let's say you cut a slice of pizza from the center and you say, well, what's the area of this particular slice? But you could actually find that out as well. So that would be, again, I'll put this in green here. That's everything inside of this this pie slice here, or pizza slice. Okay. So everything inside of that, and that includes up to here as well, of course. So what is that going to be in this case? So the area of a sector of a circle. Okay, so that's going to equal this here. So the area here, we'll call it A, is going to equal, and let me go ahead and put that down, 1/2 r squared times A. And again, same r and A that we have up here. Radius and arc length, and central angle of the arc, excuse me, in radians. Okay, so that's what we have here in this case, is those are the two formulas that are associated with those two guys. Okay, we're going to look at some examples here when we look at applications, but again, this is just for just kind of stating it. Okay, so you have those in your notes, and there you go. Okay, now I'm also going to add a little bit to this canvas here, so let me make the canvas bigger because I need more space. Yeah, there we go. Okay, now the reason why I need a little bit more here of this canvas is because I'm going to add a few more formulas here, but they're not going to be necessarily associated with the circle, but they are going to be relevant here toward using radians as a component. Okay, so let's take a gander here. All right, at this. All right, so the first one here is I want to talk about is types of speed. Okay, now the first one here is going to be relatively new if you haven't heard of it before, and that's angular speed. And I'm gonna put that in different. Okay, so what is angular speed here? Imagine if you had a tire and the tire's going around at a certain angle. Okay, you can figure out, from the central angle how fast that particular tire is, say, rotating every second or every minute or every hour, whatever the case may be. Angular speed is very helpful for us to actually compute what linear speed is. So something that linear speed, as most of you are aware of, again, like miles per hour, how fast is your car driving? Oh, my car's driving at 50 miles an hour, whatever. Okay, but angular speed here is a good medium to get you to that point. Now, what is angular speed here? Now, angular speed has a different notation here. So that's going to be W, and that's equal to A, which is the same central angle in radians, over T, where now in T here, to be a little bit more specific, is just time. And time here in these problems are pretty relative. So the thing is that we don't know what time we're going to be working over. Again, they could be minutes to minutes, seconds, okay, hours, whatever. It just depends. Now, using this here, we are going to go ahead and get we're going to get the other one here. So let's put that here for linear speed. Now, linear speed, most people are used to the first definition that I'll put here for linear speed. The first definition for linear speed, and we'll put it as V, V for velocity, so that's linear speed. But in any case, the important part here for linear speed that we do have to talk about here specifically is that you could express it the first way here, which is d over t, distance over time. Okay, so most people are pretty familiar with that. Again, you've probably used that a bunch of times. Okay, if you traveled 50 miles, in your car in a single hour, well, how fast are you driving? I'm driving 50 miles an hour. Yeah, not too bad. However, this can also be expressed here in terms of using our angular speed. So this can be rewritten as v equals rw, or again, this could be equivalent to r times a over t. So it could be rewritten both ways here. So you could actually find distance here appropriately here using the angular speed of the particular object that you're given. Okay. So there you have another couple of applications here that directly uses radians in some form or fashion. Okay. Okay. All right. Finally, for whatever reason, they also decided to put this in this section because they do talk about right triangles here, but we're going to more talk about right triangles in the next section over. However, they do talk about the Pythagorean theorem, which I think most people know by now, but still, let's go ahead and state it here just for giggles. Which color I want to put that in? Yeah, I'll put that in orange. Okay. All right. So the Pythagorean theorem says, oh yeah, all right. You get two sides of the triangle here. A squared plus b squared equals c squared. Okay. So you guys are probably familiar with that. That isn't too hard to figure out. All right, so again, if we looked at a right triangle here, here's a right triangle. Okay, and we looked at just the sides here. So we get A, we have B, and we have C. Okay, so there you go. All right, we're going to expand more upon this in the next section, but yeah, they just talk about that last part there. Okay. All right. Now that we have a good idea about all of this stuff here, all right, now that you have a good idea for this, let's go ahead and take a look here at actual problems. Okay, let's look at actual problems here, and let's see exactly what we're working with here in terms of using these formulas in some way, shape, or form. Okay, and that's going to be 6. Go to the book here. Ooh, almost signed me out. That would have been sad. Okay. Did I? Oh, whoops. Not page 80. 680. There we go. Much, much better. All right. Which one do I want to do? All right. Let's do that first. Okay. So this first one here is going to be number which one I want to do? Yeah, let's do number 4 here. Let's do number 4. Okay, so that's at the bottom of the screen here, so I'm going to zoom in. There we go. It's a bit better. All right. Sorry about that. Okay, so let's scroll down on the bottom here. We'll need to scroll to the next page here, but it says the outfield fencing for a Little League field forms a circular sector with home plate as the center. See the figure at the top. We're going to look at that here in just a second. The fence is placed at a uniform distance of 215 feet from home plate. The boundaries of the fence, which extends partway into foul territory, creates an angle of 105 degrees with home plate. At $28 per foot, how much will the fence cost? Around the nearest $10. All right. So let's look at the picture here. The picture will be very helpful here. Okay, so here's the picture of the field, okay, and the dimensions that you see there. And we want to figure out, first of all, how much fencing that we need here with this particular configuration of the Little League field. Okay, so can anybody tell me here, looking at the fence here, the blue part that you see here on the screen, what exactly are we trying to find? Are we trying to find the area of a sector of a circle? Are we trying to find arc length? Or what are we trying to find here in this case? We're actually trying to figure out arc length. That's correct. Remember, the fence here is an arc, okay, put on the outside here. So if you see it in blue, we're trying to figure out from one end to the other end, and that's going to be a big giant arc here, okay? So the fence, since it has to be kind of one arcing piece, as we see there in terms of our fencing, then yes, arc length is correct. Now, knowing that we have to find arc length here, let's go back to our formula here for just a moment. Go ahead and make this a half a page. That down. There we go. So there's our arc length here, our formula that you see here on the screen. Okay, we have, again, our arc length here is equal to the radius times the central angle in radians, all right? So let's do that here together. Put a little room here. Number 4. Okay, so let's first take a look here. We're trying to figure out here, what's our radius? What's our radius here according to the picture that you see here on the screen? What's the radius of this figure? What's the radius of the figure? What's the radius that you see here? What's that radius going to be? I know this one's a little tough. This is going to be fun. Went ahead and put a poll in the chat there. So I put a poll in the chat there if you guys are paying attention. Otherwise, I'll just sit back and relax for a while. I'll sit back with my feet up over here and be like, yeah, I can do this all day. Not exactly 52.5. That's a good guess. I would check the poll there if I were you at the top. See if it gives you a little bit of inspiration. I didn't know it was 2:15. I had no idea. But yes, indeed it is 2:15. That is true. All right. The reason why it's 2:15 is because it comes from the center of the circle here. All right, and it goes all the way out. This would be like this basically is part of a circle if you want to kind of consider it that way. So it's not a full circle, obviously, because the full fence isn't going to go around in a single circle. But still, if from the center of that center of the supposed circle all the way out to the end there, that's 215 feet straight up down the lines. All right. Now, what's A going to be here? What's our central angle here? What is A? $105. Okay. You said A is 105. Well, let's take a look at what A is, all right? Let's recall back here for just a second. Remember, A is the central angle of the arc in radians. What does 105 represent? Is that 105 radians? Or is that 105 degrees? Are you sure it's 105? Let's put a note here. You must know. There you go. Good job. You must convert degrees to radians before you plug in A. All right. So that's the trick here. All right. So the tricky part here to remember is that you have to do that first. Okay. It has to be in radians. It has to be in radians, but you don't know how to convert it. Well, didn't we have those conversions from before? How did we convert from degrees to radians? What does it say in your notes? 7 pi over 12. That is correct. Yes. So that's why we went ahead and did those conversions into radians there, JC. We had, again, to convert here, we want to find our radians here. That's equal to 105 times pi over 180. Take 105 over 180, and you indeed will get 7 pi over 12. So what we're going to do here is we're going to take, again. We're going to take 105 and multiply that by 7 pi over 12. And that's going to net us our arc length here for this particular figure. So let's see what that comes out to be. Bippity boppity boop on the calculator there. All right. We get 192.4225. Oh wait, what did I do? Oh, that's supposed to be. Oh, whoops. Sorry. You know what? That's not supposed to be 105. Sorry, my bad. I just realized my mistake. This should be 215, not 105. There we go. Yeah, I just realized that. I'm like, oh, I just accidentally took the wrong number from the wrong place. All right, let me try that again. Yeah, my bad. All right, there we go. So we get 394.00808786. Okay. Okay. Now all we're going to do here specifically is we're going to go ahead and let's go back to our problem here for just a moment. And because there was a cost for the fence here, so we now know how long the fence has to be. Well, what we don't know is exactly, how that's going to work out. So let's see here. It costs $28 per foot. Okay, so it costs $28 per foot. So if it costs $28 per foot, let's go ahead and find out what we get here. Wait, back up. Yes, let me back up here. Backing up. What can I help you with that? Okay, okay, I see what you did there. All right, so basically you want the decimal equivalent there. So let me go back to the let me go back to this. I got the decimal equivalent here because I want the exact amount of feet of the fence that I'm gonna need. So I don't want to keep the pi in this case, Jasmine. So that's why I kind of kept it like that. No, I didn't ignore pi. I just multiplied it in. That's all. So why don't you just do that on the calculator straight up? 1505 pi divided by 12, and then you should get the 394 that you see on the screen. Just multiply it straight up. I actually want the decimal answer here for in this particular application. Hopefully that makes sense there. Okay, okay. Cool, cool, cool. All right. And so for the last part of the problem here, we're going to take that 394 right there, that 394.00808786. We're going to go ahead and multiply that straight up by 28 because it costs 28 bucks per foot for the fence. So we get $11,032.23. So that's what we get here in this case. So a touch over 11 grand to build this fence in. All right, good stuff. Good stuff. Okay. All right. Let's go ahead and try the next question here. All right, got another question to go here. Another couple actually to do. Okay. So the next one I want to do here is going to be number, let's go with let's go with number 10 here. Number 10 says, if a lathe makes 25 revolutions per second, calculate its average angular speed. Round to the nearest whole number. Okay, so a lathe just kind of turns and turns and turns. If you're manufacturing something on a lathe, then of course it's going to keep turning. All right, rather fast. Now, more importantly though, is what about a lathe is what about this lathe or this problem here that's actually fairly important? And the thing I want to discuss here is 25 revolutions per second. We want to find its average angular speed. Now, we already have its time frame here, 25 revolutions in 1 second. But if we want to find its average angular speed here, let's go ahead and take a look at that. Now, angular speed here is A over T, but A here is the central angle here in radians. Okay, so we're going to need to go ahead and figure out and be like, all right, what's this central angle that we're talking about here? And how does that relate to revolutions necessarily? Okay, well, let's go ahead and put it into logical context and we'll see how it works out. All right. Now, let's answer one question here. Let's just follow logical ordering here. How many degrees, just think in degrees here for just a moment. How many degrees is one revolution? So if we go around one revolution, okay, we go one revolution around, how many degrees is that going to be? $360, that's correct. Absolutely 100%. Right, Brendan. So, now here's the most important part here, okay? Now that indeed does equal 360 degrees. But now that we've learned about radians, okay, and because the central angle here also has to be in radians, we want to convert 360 into radians. And this is going to be the important part here. 360 degrees, if you convert it into radians here, and I'll skip doing the work here for this one, is equal to 2 pi radians. So 2 pi radians here is equal to 360 degrees. So what that means is that one revolution, if we look at it from a radians perspective, is equal to 2 pi radians. So basically what we're doing here is we're going to use this small little conversion here, and we're going to find the average angular speed here using that little conversion of one revolution equals 2 pi radians. Because again, angular speed here is, again, A divided by T. So we start off with 25 revs per second. We already have the time put in. Now all we have to do is multiply, put one revolution here on the bottom, cancel that, and put 2 pi radians here on the top. And so here we just have, again, 25 times 2 pi, whatever that is. They want a decimal equivalent, we'll go ahead and put that down. All right, so that's 157.08 radians per second. Okay, and that's actually the average angular speed of this particular lathe. Okay, so that's what it's asking you to do there in that case. Any questions about that one? That one there is actually nice and straightforward, so. Nope. Okay. Okay, let's go ahead and show off one more here. And let's do a linear speed one. Okay, let's look at this one here. Now it's just number 8. So number 8 says a pulley with a radius of 36.2 centimeters rotates at 6.5 revolutions per second. Find the linear speed of the belt driving the pulley. Okay, so now we have a pulley here. We actually have a radius thrown in. That's 36.2, and it rotates at 6.5 revolutions per second. Now, from number 10, we now understand that 1 revolution is 2 pi radians. Okay, so all we have to do here is what we need to do is first figure out the angular speed of this particular pulley using the 6.5 revolutions per second. And then we're just going to multiply that by the radius of this particular pulley, which is 36.2. So what we'll have here specifically is, let's go ahead and showcase the problem here. Let's first convert a couple things over here. So I'll come back to that in just a second. Just gonna zoom out here. Okay. So back here for a second. Okay. I just need the numbers there. Need to make sense of it, of course. Number 8. Okay. So here we have 6.5 revolutions per second. So with 6.5 revolutions per second, we're going to multiply that by the same, again, 2 pi radians like we did in the last one over 1 revolution. Okay, now we have the radians there, and that's perfectly fine. And now all we want to do is multiply this by 36.2, which is the radius here in this case. We'll put 36.2 over, so 36.2 centimeters. I want you to note here that radians don't really matter as a unit in terms of the linear speed. You're just going to basically ignore it and just get centimeters per second here as part of your final answer. That's typically what you do in pretty much most of these problems. So don't worry about radians being a second unit here that kind of hangs around. It really doesn't do anything in terms of its linear speed. We only focus on the 2 units that we see here that are centimeters and seconds. You don't have to really worry about this part here too much. All right, so let's go ahead and do this out here. We have 6.5. 6.5 times 2 pi times 36.2. Okay. All right. And so if we do this out here, we're going to get 1478.43 centimeters per second. Okay, there we go. All right, nice. Any questions about that? No? Okay. So hopefully that's not too bad. Okay. All right. So those are the questions I kind of wanted to do from that section there. All right. So that's section 10.1 in a nutshell. All right. Takes a little while to explain because there's a lot of, like I said, a lot of different concepts that we go over here. So hence why I just want to talk about it here. All right. In any case, we do have a second section that we do have to go over here. So let's talk about that as well. All right. So what is section 8.2 talking about here? All right. Or section 10.2, sorry. Can't spell trigonometric off the top of my head. Let's see. So let's talk about trigonometric ratios here. This is the start of really defining trig problems. Okay, so we're going to be in this section here. We're going to be talking about a few things here specifically regarding trigonometry and defining sine, cosine, and tangent. I know that those are not three things you want to hear out of my mouth, but well, that's just kind of the reality of the situation. So let's take a good look here at how we can go ahead and define that. Link this out here. Bye. All right. Okay, now in this particular case, when it comes to trigonometry, the first thing that we have to do is we have to understand triangles. And specifically here, we need to understand the right triangle. So we're going to look at a right triangle here on the big screen. Okay. All right, so we're going to have a right angle here, okay, right here. And this is going to be a little bit deliberate, the way I'm going to kind of showcase this off. So here we go. We have a right angle right there. There we are. Okay, now, there are three sides and three angles to the triangle, okay? However, the way you want to set up a triangle here is very specific. Now, what do I mean by that here in this case? Well, if I want to be as specific as possible, I'm going to label my three sides here. Let's say I have A, and I have little a, little b, and little c. All right? These are my respective sides of the triangle here in this case. Okay? Make that a bit bigger. All right. Now, more importantly here with A, B, and C, we want to find where their respective angles are going to be as well. And this is a very important point here regarding triangles, especially any triangle. But in our case, we're just using right triangles. But nevertheless, is that one thing's to note here, that angles are always opposite their respective side. Okay? Angles are always opposite their respective sides. So I'm going to put this and say, let's say I put this in, I'll put it in blue here. But let's say here's letter A, okay? Here's little a. Now, if I want to find angle A, and this note here has to be true, that means angle A has to be opposite that of where little a is. All right, if B is down here, then big B has to be opposite, or up here, about where, excuse me, where little b is. And here we have little c, and we have big C down here, just like so. Okay? So again, this is actually the way to design a triangle. So A, B, and C just can't go all willy-nilly, and neither can the angles. They have to go in specific places. You could put, again, A down here, and big A would be up here. You put little b over here, big B would be over here. It always has to be deliberate in terms of where the angles go. They always have to be opposite of where you actually go ahead and place those letters. All right? No ifs, ands, or buts about that. Now, now that we understand that here, what we're going to do here specifically is we're going to go ahead and define the trigonometric functions here based on this right triangle. And we're going to add a little bit more to this, of course, so it can be, we can look at it from a proper perspective. Okay. So the first thing that I'm going to do here is I'm just going to go ahead and look at this angle right here. So this angle here is angle A. All right, so the one I've marked here in purple, we're going to put that in angle A. All right, that's what we want to do here in this particular instance. Now, in order for us to actually memorize this, or at least kind of get to know it a little bit, you probably heard this before, but I'm going to reiterate it here once again. And that is, we're going to use this following acronym here. TOA. Okay, so we can use SOHCAHTOA here in order to help us define what sine, cosine, and tangent are going to be on a right triangle. All right, so let's talk about it this way, and I'm going to shrink this down, and we'll look at our right triangle here. Okay, so this will be helpful here for what we're going to do next. All right, now let's look at S. S and SOH, okay? So it says so, SOH. So, or the S in so stands for sine. So let's look at sine. Now let's say I'm looking at the angle A here. So this angle right here. So sine of A here is going to equal O. O represents the word opposite. So opposite, okay, which is right here. So this is opposite here. Divided by H. Now H represents hypotenuse. Where's the hypotenuse? The hypotenuse is the long diagonal between in the right triangle. So the long diagonal that you have there, this side here is the hypotenuse. Okay. So that is sine. Sine of A, sine of angle A. Let's look at cosine. Cosine of angle A. That's the ka part in SOHCAHTOA. Now the first letter there is A. What does A represent? Well, A represents adjacent. Okay. And H here represents once again the hypotenuse. Now let's talk about adjacent here for just a second. Adjacent is just a super fancy word that just means next to. Okay, so that means here's angle A. What's the side next to angle A? Well, that happens to be this side right here. So adjacent would be down here. Now, let's look at tangent, TOA or TOA. Well, O represents opposite, and A stands for adjacent. Okay, and we've already labeled all three sides here so far. So there we go. Now, if we put these in terms of the letters that we see here on the screen, like our A, B, and C that we see on the screen, let's go ahead and label these here. So here we have opposite over hypotenuse here. Well, that's going to equal A over C, so A divided by C. Adjacent over hypotenuse here, that's going to be B over C, B divided by C. And then finally here, tangent here specifically is going to be opposite over adjacent, so A divided by B. Okay. So that's what we have here in this case. Okay. Now, there is a second half to this, and this is the part where I need to make a very important note for this particular part. Note that the opposite and adjacent sides can switch depending on which angle you use. Okay, now why do I put this note here? Because I've written opposite and adjacent here, okay, just as such. By the way, the hypotenuse never changes, so that's what's very convenient about that. That's pretty static, set in stone. But the opposite and adjacent sides can switch depending on what angle you use. Well, you forget there are two angles here that we actually have to we can look at here, and that will net us slightly different results. So the second one here that we're going to look at in particular is going to be big angle B. Put that in green. Big angle B offers a different perspective of how we can define opposite and adjacent. So if we took a look here at this case, let's say I did here sine of big B instead of sine of big A. Well, I'm going to use the same, again, the same rule here. I'm going to have opposite over hypotenuse. That part is true. But now the side that is opposite big angle B is now this side right here, which is on the bottom of the triangle. So marking this here as opposite, this is opposite for B. Oh my gosh, come on. Stop being derpy. All right, thank you. Okay, and that means by default here, over here is now adjacent. So for angle B. All right. Okay, so we have opposite and we have adjacent, just like so. Okay, so now for sine of big B, sine of big B is opposite over hypotenuse, but now that's going to be equivalent to B over C, B divided by C here. Cosine of big B here is going to be equivalent to, let's see here, we have adjacent over hypotenuse, so we have here A over C, A divided by C. And then finally, we have tangent of big B here. And tangent of big B here specifically is going to be, again, opposite over adjacent, or B divided by A. So as you can see here, let's blow this up here for let's zoom back actually just a second. You can see the difference here. The difference is quite stark. Okay, that's definitely true. All right, is that we have sine, cosine, and tangent here specifically. But again, they're very different than that of their sine, cosine, and tangent counterparts that we had from before. Okay. Any questions about that? Yeah. Okay. All right. So let's take a good look here at an example. Okay. And let's use this example to figure out some of the problems. Okay. So back to the book here. Page is that? 90. Okay. So here we see some triangles. All right. And we're going to go ahead and work with this here together. All right. And we'll see exactly how it works out. Let's go ahead and give one of these a try. All right. Okay. Let's take a good look here. It says calculate the ratio here for tangent of 31 in the triangle to the right. Okay, we don't need to use the calculator for this. You're just going to use simple observation of what you see here. So tangent is, what's the definition of tangent on a right triangle? What's the definition of tangent on a right triangle? Okay, 33 over 56. So again, if we look at this carefully, all right, here we have, sorry, I didn't mean to click the radio button there. But yes, we have opposite over adjacent. That is the TOA part of tangent. So TOA here. So let's look at that here just really quick. I'm going to give myself a little space down here. So looking at this picture here, we have tangent is equal to opposite over adjacent. And according to this triangle here, well, we have tangent of 31 degrees, since that's the angle we're given here. Is again opposite here, happens to be 33. That's the opposite side that you see here on the triangle. Oops, sorry. Over adjacent here, which is 56. So our final answer here should be letter B, as we see there in this problem. Check it. Got it. All right. So far, so good. Go ahead and click out of this. Well, let's try another one. Where is it? There it is. Okay. How about this one here? What is sine of 43 degrees based on this right triangle? What is sine of 43 degrees based on this right triangle you see there? (34 over 50). Okay, good. So using sine, the so part, sine here is equal to opposite over hypotenuse. So the opposite side here of 43 degrees is 34. And the hypotenuse here is 50, the long diagonal. So we're going to get B here as our answer. All right, very nice. Very nice. Now let's try one more here. How about this one here? What's cosine of 63 degrees? What is cosine of 63 degrees? (27 over 60). Okay, let's take a look here. Again, cosine here is equal to adjacent over hypotenuse. So the adjacent side here is going to be 27, and the hypotenuse here is 60. So indeed, that's correct. So we get 27 over 60 here. There we go. Let's check it. And we got it. Good job. All right. And again, sometimes they'll ask you for this. Just do 27 over 60 as a thing. So just basically all they're asking you is just to do 27 divided by 60 here, and you get 0.45. All right. Okay. All right. Okay, good. Are there any questions about that? Okay. No. All right. So I'm going to call a slight audible here, And this is kind of this is basically 3/4 of the way through the second section. There's one more part here to this section that I do want to acknowledge, but I'm going to start next time on that because that has more relevancy in section 10.3. And I think I've given you a lot of information already here today. So we'll be coming back to this, of course, but we'll be working with our calculators here a lot here for next time. So uh, we'll talk about kind of the latter half here of this section here, and then we'll apply that directly to section 10.3. So I think that's going to be the most prudent way of just putting in relevant material, but I don't want to keep adding in more and more and more information that I don't feel would be necessary for today. So we'll finish up here with this section here for next time. Okay, doing the kind of the last few examples here for this. We'll again use our calculator for this, but again, you could go ahead and try the problems here on 10.2. You could do like 3/4 of them. There's only one problem there that you probably will have a tough time doing. So, and we'll talk about that and where that's relevant for the applications there in section 10.3. So we're pretty much going to finish next time. It's just a matter of I just want to include one thing probably in the next class as opposed to this one. That's about it. So, all right. That was a lot of information today. So, and I want to like overwhelm you even more. So, yeah, a lot of stuff. No problem. I'm here to help. All right, guys. Again, continue working on the tests and homework or whatever you want to do. Again, we're going to finish up here with chapter 10, the last section of the textbook here for next week. Okay, I want to thank you all again for coming on out here to the stream. You guys are all lovely, all wonderful people. And I look forward to seeing you guys here next week. All right, the last couple classes of the semester, if you can believe it. So, yeah, we're getting there. All right, we'll have a lot to talk about here though for next class, and then talk about the time frames and whatnot. So got a lot to talk about, a lot to do, but again, it's nearing the end of the semester, so it's going to be a busy time for us. So, all right, great job, everybody. Thank you all again. All right, and again, have a wonderful weekend. Please enjoy the. What about the test? Which one? The chapter 6 to 10 test? Or are you talking about the final exam? I can answer either of those questions. Oh, okay. No, that's a fair question. Let me go over here for just a second. Should be listed on there, but okay. So as you can see here, the final exam and the last test are both due on the 18th. Okay. So, Dr. Dan, that should answer your question here. On the 18th, there is when that is going to be due. Both, yes. Again, though, you probably want to give yourself some time because there are 50 questions on this chapter 6 to 10 test and 50 questions on the final exam as well. So I just basically took half of the first half of the test and I took half questions from the second half of the test and basically threw them together for the final exam there. Again, as you see, I gave you a lot of time. So I gave you 480 minutes. I gave you essentially 8 hours and 3 attempts for the chapter 6 to 10 test. And you get 3 attempts for the final, and you get 10 hours to finish that. So, yeah, there's also practice test as you can see there on the screen. So you can take that as many times as you wish. Any other questions? Will there be a practice test for the final? No. So that's a good question there, Brenton. No, there won't be a practice test on the final because all I did was take 25 questions from the first exam and 25 questions from the second exam. So if you want a practice test there, basically try the problems from both of the subsequent practice tests, okay, that you see for each half of the book, and then that will give you a good idea. 50 out of those 100 questions will show up on the final exam. So that obviously not the exact numbers, but questions like it. So I basically played eeny, meeny, miny, mo with their with your two tests to make up the final there. Obviously, I wouldn't want to do 100 questions, but 50 questions is fair for a final. That will cover pretty much everything I wanted to talk about. So if you want to practice with that, that should be there just for you. Any other questions? If you take a look there at the screen, Dr. Dan, the answer is no. You get 3 attempts. So if you don't do so hot the first time you try the final, you get 2 more tries after that. Again, up until the deadline, so I don't suggest you wait until the last minute to do it. Otherwise, you're going to waste the attempts that you probably would have had. Oh, okay. Sorry about that. All right. Any other questions you guys got? No? Okay. Very good then. Okay. Great. All right, guys. Thanks again very much. I'm glad you guys are asking questions and whatnot, just kind of clarifying things. Again, if you have additional questions about the exam, feel free to email me or just ask me next week. We got lots of time between we got lots of time between then and the very final day. So go ahead and do so. The last two classes here will be next week. All right. In the meantime, everyone enjoy your weekend, and we will see you all next time. Okay. Take care of yourself, and we'll see you. See you then. All right. Have a great one, everyone. Take care of yourselves.